Self-inductance. So let's take the same three cases which we have just seen. So instead of loop, let's take a coil, and instead of the EMF distributed among the loop, let's replace that whole thing with a battery. So all the three cases now we can draw in a simplified form. So here, when the current is constant, the current is still constant, I naught. Here when I is changing, a battery opposing the increase in current, so in a negative sense, is there. Here the battery is in the positive sense, so it's in the direction of the current. So same thing we have done here. Here the battery is in negative sense, here it is in positive sense. And magnitude of EMF is d phi by dt. So now let's write these equations for these things. So by Faraday's law, we know EMF is minus d phi by dt. And also we know that the flux induced in the loop is proportional to magnetic field, and magnetic field is proportional to current. So I can directly say that phi flux is proportional to current, or I can write flux is L times I. So proportionality constant is L. From 1 and 2, I can take the value of phi here, and I will get EMF induced is minus L di by dt. So this value of E, which we were writing d phi by dt, now we can write as minus L di by dt. This ideal solenoid coil is also called a inductor, and L here is called self-inductance of the coil. Its SI unit is Henry. So this self-inductance, or L, and the proportionality constant depends on the construction of the coil, like how many loops it has, what is the radius, what is the material it's made of. So experimentally we can find out that if we supply I current, how much phi is going through the coil, and accordingly we can come up with the L. So yeah, this is self-inductance of the coil.